Howdy folks, Mr. Reed here, and welcome to one more question. So today what I'm going to be taking a look at is solving exponential equations, but we're going to kind of do it a cheesy way that only works for specific types of exponential equations. This is because we don't really, at least not in my series yet, and the order I cover things in my classroom, have the logarithm to deal with exponential equations yet. So if you haven't seen a logarithm yet, you're in the right place if you still need to do a little bit of fiddling around with exponential functions. So let's see how that goes. Let's get to it. Alright, so what I have up above is an equation, and there are only a very particular type of equation that can be expressed in a certain way that we'll be able to solve right now. Basically, what we have to be able to boil it down to is having our left-hand side and our right-hand side being such that they can be expressed as the same base, a single power of the same base. So in my example up above, I have 27 and 81. Both of these are powers of 3. Now, that's not the only power that they can be written in by using some sort of rational exponent, but 3 is probably what comes to mind the easiest for me. So where I'm going to start is just by copying that down. So we have 27 to the power of x plus 2 divided by 3 and is equal to 3 times 81 to the power of 1 minus x. So that's 81 is the only part that's to the power of 1 minus x. The 3 is kind of by itself as a coefficient on the front of that particular statement. And then everything, the x plus 2 over 3 is in the exponent position. I kind of did a bad job of writing it high enough to make that clear, but we'll make it do. All right, so one of the first things we can do is any number that is not a 3 that we can represent as a base of 3, we can switch that over right away. So 27 is actually 3 to the power of 3, and that's still all raised to the power of x plus 2 to the power, over 3. On the other side of my equation, I have a 3 already kicking around, but then I have 81, which is actually 3 to the power of 4. So 3 times 3 is 9, and then 9 squared is 81, so that's 3 times 3 and another 3 times 3 for 3 to the power of 4. That is to the 1 minus x. Now, I can use some logarithm rules to kind of continue to pick away at this. So the first thing I'm going to do is to say that over on my left-hand side, I have these a power with an exponent, of course, raised to another exponent, and there's a rule that allows us to take those exponents, multiply them together to create a single exponent instead. So I have 3 to the 3x plus 6 over 3. Now, I did a kind of an oopsie-doo there. I was multiplying by 3 and dividing by 3. I could have just canceled that. So on my next line, I should wind up with just x plus 2 as the exponent. I shouldn't have got sidetracked there. Anyway, that's fine. On the other side of my equation, I need to deal with the exponent on the bracket first before I can start trying to tuck that 3 inside. That's on the front of that statement right now. So again, that is a base of 3 to the exponent 4 raised to another exponent. So we do a multiplication there. I leave my 3 alone on the front, and I'm going to get 3 to the power of 4 minus 4x. So we can take that and simplify it on the right-hand side a little bit more, because if we have two things of the same base, two exponential statements of the same base that we are multiplying together, we can add the exponents. So I'm not going to go over all the exponent rules. If you want to find those out somewhere, if you're not familiar with them, you should look them up. Maybe someday I'll make a video on those. But for the time being, I'm assuming that you're comfortable with that part. So as I said, 3 to the power of 5 minus 4x. And so we have something that is now a single power function on both sides of the equation. Single exponential function, my apologies, on both sides of my equation that we have the same base. So that is really, really, really important. If we were to take a look at this type of function, a single one that's just written as some combination of horizontal changes. So in the case of the left one, that is going to be a shift of 2 units to the left. And the right one, that's actually a horizontal reflection, a stretch of 1/4, as well as a shift of 5 units to the left. So because of that, we can kind of get an idea of what these look like. So a normal exponential function is going to go through 0, 1 here, and it's going to grow really quickly up to the right because these are both bases that are greater than 1, and it's going to have the very low values as it goes out instead to the left. So that's kind of the shape that it has. All we're allowed to do is basically stretch it this way or slide it this way. So if I want to have another equation that's here, and I kind of have it so it's slid over a little bit, now that actually isn't slid over. I'm going to try that again. So it would be more like that. Then you can see how it would have maybe one intersection point. Without being able to move this thing up or down and kind of rotate it so that it was flipped, I guess, so vertically instead, I'm not going to be able to clip this thing twice. Not with a linear function up in the exponent position, which is basically just simple transformations, only in the horizontal sense. So because of that, we're expecting there to only be, these are actually 1-to-1 functions, so there's only one y value for every x value, but there's also only one x value for every y value. Because of that, if these two things are equal to each other, and this is super important to being able to solve them this way, if these two statements on the left and the right are equal to each other, then their exponents must be the same. Because the bases are the same, the only chance for them to be equal to each other up top is if they actually have the exact same value. Because 3 to the power of 2 can't be equal to 3 to the power of 5 or 3 to the power of -1/2. It just doesn't happen like that. There is only one y value for every x value and vice versa. So if they are in fact equal, and we can find out if there is a point like that out there that exists, or an x value, then we need to make sure that we acknowledge that they have to be the same exponent. If they are the same exponent, then we can write down x plus 2 is equal to 5 minus 4x. We are setting that to be true because of what the behavior of these functions is like. Great, that's actually really wonderful for us because we can just solve this linear equation by adding 4x to both sides and then subtracting 2 from both sides, and then I can say then that x is equal to 3/5. So we have a value for x that should work. If we wanted to, we could fire that up into the initial equation, but we don't really have to because there's nothing that we've done that would cause this to be an extraneous root. Both of these exponential functions are defined over all real numbers. Their domain is XER, and so if we solve for an intersection value and nothing's gone wrong, then that should be okay. So that's really all there is to it, and that's the only type of one we can do without involving logarithms. So if you want to do some more flexible solving of exponential functions, you're going to have to wait until I pump out a few videos on logarithms, and then we'll be able to come back to this idea and solve a much greater variety of equations that are set up like this. The time being, if you can write the bases, write your exponential statements using the same base, you're going to be okay. You just do it like we did it here, and you'll be able to solve them. Hopefully that was helpful. As always, like, subscribe, and take care, folks.